So yeah, let me show you. So we have secant squared, cosine squared, tan squared, and sine squared. Yeah, and if we can find coefficients to each one of those four coefficients, C1 through C4, where at least one of them is non-zero and yet they all add up to 0, then we can say that they're linearly dependent. If we can't, and C1 through C4 has all to be 0, the only way to make it 0 is if they're all 0, then they would be linearly dependent. You agree? Okay, now notice that cosine squared x plus sine squared x. Right, then it will be linearly independent. Okay, and so here we have secant square x plus tan squared x, yeah? Okay, and then I'm supposed to put a C1 here, a C2 here, a C3 here, and a C4 here. Now watch. Cosine squared plus sine squared is 1 technically. So if I make C1 equals 1 and C2 equals 1, then those two would add up to cosine squared x plus sine squared x. They would add up to 1. So now the trick becomes, if I can find coefficients that makes those minus 1, then they would add up to 0, yeah? Well, I know from TRIG that secant square x equals 1 plus tan squared x, which makes tan squared x minus secant squared x, or tan squared x minus secant squared x equal minus 1. You agree? Because if I move this around, I would get tan squared x minus yeah, tan squared x minus secant square x equal minus 1. You agree to that? So if I make C3, to be minus 1 and C4 to be 1, because that would give you tan squared, minus secant squared, then this sum here would be minus 1. Then this sum here, if I let C3 equals 1 and C3 is minus 1 and C4 equals 1, then this sum is minus 1. And when I add 1 and minus 1, I get 0. So I was able to find C's, right? I was able to find C1 equals 1, C2 equals 1, C3 equals minus 1, and C4 equals 1, where they add up to 0. Where all of these functions here add up to 0. So therefore, linearly dependent. Does it make sense? It's very simple, what I did. I made cosine squared plus sine squared equals 1, and secant squared plus tan squared add up to minus 1.
So two of them, cosine squared and sine squared, are not linear. But when you add them together, and when you add secant squared, tangent squared.
Right.
Secant squared and tangent squared are linearly dependent with sine squared and cosine squared.
Right. They're all together linearly dependent.
But secant squared and tangent squared
are
not.
Right. They would not be because, yeah, they won't be. But in this case, you can sum them up in such a way that cosine squared and sine squared is 1, and secant squared and tan squared negative 1 by choosing the right coefficients. 1, 1 on C1, C2, C3 negative 1, and C4 is 1, because tan squared minus secant squared is minus 1. So that gets you minus 1, and 1 gets you 0, and they go.
So certain sets are sets of equations.
So that's how you use the definition of linear dependence. You can't use the Wronskian on this because they're linearly dependent and they're not set of solutions of an ordinary differential equation. So you do have to do it using the definition.
Yeah. So these are there are two sets of equations.